Hello friends, it's Ben again. So this is a video for Calc 1, and this is one of the most important things that we will look at, even though the notion of it is actually pretty simple. The thing that we're trying to look at is the idea of limits. So you have a pretty good notion of limits as it is. If I have two objects and I talk about the distance apart and I cut the distance apart in half and half again and half again and continue doing that indefinitely, you hopefully realize you never actually get the two objects to come together, but they're close enough for practical purposes after a while. So that's really the notion of a limit. You are looking at anticipating where something is going towards without actually evaluating it by just plugging in a calculator. Okay, so that idea of a limit and adding it to the things that we could already do algebraically is something that came up in the, I want to say 16th, 17th century, right around the time of the Enlightenment, and it changed science completely. This whole idea of being able to change numbers and have kind of a guess as to where things are going at, really, it was a paradigm shift, huge. And so, right, we're going to look at several examples. They are somewhat like what you'll see in your homework. I'm trying not to just do exactly the same thing, but they will be similar. So let me grab my picture there to put it out of the way. And then I'm going to put this Zoom meeting thing out of the way. All right. And then I'm going to share screen with y'all. And the screen I'm going to share is a Desmos graph. And the graph that we're looking at here is this y equals x cubed minus 4x. Okay. And as a matter of fact, I think I'm going to go in there and adjust that a little bit and maybe zoom in. All right. And I think that's good enough. Okay. So this point right here of 2, 0, what we're going to do is to figure out what the slope of a tangent line is right there. So a tangent line, as you know, should intersect a curve locally in just one point. What I mean to say by locally is that if you zoom in really close on it, you want to have it coming along to the graph in such a way that it touches it, but it doesn't actually go through it. Okay. Yeah, and my definition there probably does not suit a good etymologist or even a good mathematician. But with the picture that you're looking at there, we need to get an idea of what to do. So the thing we're going to do is something very algebraic and something that you've dealt with a little bit before. We're going to write an equation here, y equals mx plus b. Okay, so for that we need sliders for both m and for b, and I'm going to zoom out a little bit. And as you can see, the mx plus b that we've got there is not going to line up very well. And I can take the b, as I'm sure you know, and slide up and down and get my intercept. And then I can take the m and slide up and down to try to get my slope to match in. Okay. But actually looking at that, I don't think I want to do it that way. To heck with this, I'm going to cut those out and I'm going to add something different in there. Do y'all remember the point slope form of the equation of a line. So the point slope equation of a form of a line says y minus y sub 0 equals m times x minus x sub 0. So x sub 0, y sub 0 is the point you're talking about. We need this to go through the point 2, 0, right? So we are going to do y minus 0 equals m times x minus 2. Close parentheses, and now we'll add a slider of m. Do you see why I did that instead? Now, knowing that, I only have to match up the slope. And I think I'll try to zoom in pretty close there. And it looks like we can push the slope up and up and up and up and up. And pretty soon, it looks like we may have matched it pretty good. But let's zoom back out and see. Yeah, it's looking like that 7.7 is looking all right for it, right? And I think that for my stuff that I want to do here, I'm going to change the y that I'm talking about here so that I'm maybe only talking about the y values from, negative 0.2 up to positive 0.2, something like that. And then I think my x values, I'm going to have to zoom those in quite a bit as well. So maybe from 1.9 up to 2.1, right? Now at that point, you can see hopefully here that we're not quite tangent with this, okay? And so I'm going to take and nudge this on a little bit farther. And it looks to me like when I hit 8, it looks like that is going to be a little bit closer to tangent. And then I can try to zoom in and see how does it look now. It actually does not look quite perfect to me. And I'm leaning off to the side and doing a calculation that y'all can't see in order to check myself. Yeah. Oh, I see what the problem is. Y'all probably caught this and I didn't. I have it set at 7.9. It's actually supposed to be 8. Okay. So insofar as looking at this and stuff, now it's actually got perfectly exactly the right answer. But you should rightfully be asking, how the hell am I supposed to know? I'll zoom in as best I can, right? And do the best you can on this sort of thing. We're trying to get the idea of a tangent line from doing something with the sliders. And if you'd like to work with it in the form y equals mx plus b and mess around with the sliders quite a bit, you can go ahead and do that. But with the way that I've messed around with it here, I can now see that if m is going to be 8, then if I turn that off, maybe I can say y equals 8x and then minus 16. And it looks like that is setting in there perfectly. So for an answer I would give on this sort of question, it's going to be y equals 8x minus 16 for the line. Or if all I'm asked is find the slope, then I'd just say m equals 8. Okay. Now, if you don't get it perfect, that's fine. Okay. But get it as close as you can. All right. Okay. So then the next, well, okay. That is a concept that we will refer to as the derivative. It's going to come up later on, and it is a consequence of limits, right? So the next thing that I want to share with you is an idea that's referred to as velocity. So what we talk about with velocity is actually going to be a rate of change. So let's screen share here again, and hopefully this time it'll work on the iPad. 1, 2, 3, 4. Yay, it's going to work. Okay. So here we're given a problem. The position of an object at a time t is equal to s of t equals 4 plus 10t minus 4.9 t squared. Now, if you've done some physics before, you recognize that that 4.9 is 1/2 of 9.8. So in other words, we've got 1/2 gt squared appearing in here. The 10 is going to be the initial velocity of some projectile that's being fired upward. If it was being fired downward, then it would have a -10 instead of a +10. And the 4, it's going to be fired from a height of 4 meters tall. Okay. So we're going to approximate the velocity at the time t equal to 2. Now, you can certainly go along here and say s of 2. You can find out what the height is at time 2. 4 plus 20 plus, let's see, what is 4 times 4.9? 19.6, I think. So we get 43.6 meters high. But doing that sort of calculation is kind of time consuming, right? So what we would like to do is to do that calculation in the most expeditious way possible by making a machine do it for us. So I will share a different screen with you. And this screen is to a spreadsheet. So if you, can I zoom in? Come on, guys. That's supposed to work better than this. All right. So I'm zooming in here. I've given it a bunch of t values. I'm going to have it calculate then the s of t that goes with those t values. Okay. Now, I've done a lot of stuff with spreadsheets. You may not have done as much. Okay. So I have went ahead and lined up a bunch of t values over there on the left. And then I'm going to use a trick with spreadsheets to tell it to calculate using that thing over on the left. I hope this is going to be big enough that you can read what I'm writing. I'm going to type an equal sign that says I'm going to type a formula. And then 4 plus 10 times, you have to type the asterisk. The computer doesn't understand it if you don't. And I'm going to reach over there and tap the t of the 0 there. And then I'm going to say minus 4.9 times. I'm going to tap that same t again. And I'm going to put a caret for the power and 2. And I hit enter. Okay. Now, I did not know that the computer is going to do this. It suggested an autofill for me to actually put in these numbers. And I'm spotting, by the way, that earlier when I had that 19.6, it was actually supposed to have been a negative 19.6. Darn it. So I'm going to go ahead and I'm not going to autofill here because I want to show y'all how to get the autofill to work. I'm going to highlight that place that I did the calculation. And you can see that it's got a little blue square in the lower right-hand corner. If you grab that, it will turn into crosshairs. And when you drag down, it will fill a formula in that constantly says, I want to use that formula that is off there to my left. And so it's going to do the calculation with the t equals 1 and get 9.1, and the t equals 2 and get 4.4, which I know you think that I got 43.6, but you are totally misremembering that. And that was supposed, I got 4.4 meters. That was exactly what I had. Sorry. Okay. Anyway, though, this illustrates why it's better to let the machine do the calculation for us, right? So what you can tell from looking at this, and if you graphed it, you could see it in a different way, is that this starts at the height of 4, and it goes up, and it must be continuing to go up and then go down somewhat, and then it'll go down and down and down, okay? Those are not velocities, those are the heights. How do you get the height, right? How do you get the velocity out of this? Well, velocity, you take a change in distance and divide by a change in time. So since we want to do this at about, what did I say? T equals 2, we're going to go over here and I am going to put in T equals 2 to all these spots here, right? And then I'm going to take these delta T's. Where did I get those from? I just made them up. They need to be small numbers and they need to get smaller as we go along. That's all the difference. And now I'm going to tell this equals the T, which is to my left, plus the delta T, which is another space to the left. And I'm going to go ahead and let it autofill here. And so you can see how 2.1, 2.05, and so forth, they're just taking the T and adding them on there. Now, I'm going to use this formula that I had over here. I'm going to copy it. So I just highlight and Command C. And then I'm going to bring it over here, Command V. And you'll want to check and make sure that it's getting the right T values. It is using in the formula G3, which is the T that's right beside it, okay? And then you can copy that on down as you like to, okay? But then we're going to also need S of T, and that's a little bit of a hassle. So I can paste in the same thing as before, but now if you look at the formula, it's using H3, which is actually my S of T plus delta T. But I can take and edit that and just delete that H3 and put the F3 in instead. And I have to do the same thing for the other F3, or for the other H3. And I managed to not do that. So I will by hand delete them and put F3, okay? So 4 plus 10 times F3 minus 4.9 times F3 squared. Okay, yeah, that sounds right. So notice that you have a fairly big difference between the two of them there when the delta T is 0.01. Now, if I go ahead and drag this down, you'll see that when the delta T is getting less, then you are getting values that are closer and closer to each other. So I'm going to tell it equals. Now I want to subtract these. So I say equals, I click on where the S of T plus delta T is, minus, and the S of T, and I hit enter. It wants to autofill, and those autofills look reasonable. So I'm going to go ahead and select them there. And then here is the place we're going. We have the difference in the heights, and we're dividing by the amount of time that passed, the delta T. So we will say equals parentheses, and we'll just grab that right over there, the S of T plus delta T. Oh, I guess I didn't need the parentheses after all. Okay. But divide by, now we have to go back and find the delta T over there, and then we can hit enter. It wanted to fill in, and I clicked the wrong thing. Okay, clicking in there, and I'm watching what's happening. This T, as it gets, this delta T as it gets smaller, is going to make this difference quotient, that's what we call it, go towards some value. We got -10, -9.8 something, -9.6 something, -9.6 something. Notice it gets closer and closer to -9.6. So the velocity that we're going to guess out of this is -9.6. I guess it would be in meters per second. okay? So you'll do something similar in the problem that you're looking at. If you see that the values that you're getting like that are not going towards a single number, there might be something going awry in your calculations. So if you need to ask me about that sort of thing, you will have to give me edit privileges so that I can look at your spreadsheet. So this is why I would suggest using Google Sheets, because if you're going to insist on using Microsoft Excel, I don't know if I know any way to get hold of it. If you're saying, well, I'll just share my screen with you, great, but I can't control the cursor on it. So anyway, though, the thing that we were looking for velocity was going to negative 9.6 meters per second. And I'm going to try to remember to give you all a PDF of the notes that I'm writing here. And I will paste a clip of what I just showed you there. So, all right, so those are ideas that we're heading towards, and we're going to talk about what we do for them with some other problems. Okay. Oh, I forgot to do something. Let me share screen again, because there's something that you probably know how to do, but just in case, I'm going to remind you. So if I had that same sort of problem here, it said the position at time t equals 0, when will, wow, let me edit this. When will s of t be equal to 0? So that means that you've got some object that has gone up in the air and come back down, and you're interested in how much time will pass before it comes back to the ground. So the trick in this is to just pay attention to what it's actually asking. So if I want s of t to be equal to 0, that means I want 4 plus 10t minus 4t squared to be equal to 0. And I wrote 4t squared when I meant 4.9t squared. That's very embarrassing. But if you had written that in this order here, it would probably look a lot more familiar. We're just talking about solve a quadratic equation. So your t is going to be negative b plus or minus the square root of b squared minus 4 times a times c, all into that square root, and all of that divided by 2 times negative a. Okay. So when you do that, if you're like me, you're going to need a calculator to do it. And so I'm going to just real quick do that on the calculator. So what did I say? Negative 10 plus the square root of, let's see, that'll be 100 plus 16 times 4.9, close parentheses, divided by the negative of, let's see, 2 times 4.9 is 9.8. Okay, so one solution is t equals negative 0.3. I'll go ahead and put 3 digits past the decimal, negative 0.343. And then the other solution, the one with the minus on it, will be t equals positive 2.383. Okay, and remember how on some of the problems in the last assignment we had extraneous solutions? This one's extraneous because of physical sorts of constraints. You can't be talking about negative time. We're only looking at the problem for positive time values, so we throw that out. Okay, so the t value you're looking for must be approximately 2.383. And You have to look at the problem and see how exact do I actually need to be, right? Okay, so that is that, and then we're going to look at basic limit laws stuff, okay? So basic limit laws, what we're talking about is that if you have a function and you looked at the graph of the function, and I guess this one's a parabola, right? Then it would look maybe somewhat like this. I have not made any effort at all to make this very exact. But if you're talking about the limit when x equals 1, what we're talking about is approximately what are we getting close to as the x gets close to 1. All the functions you have dealt with in algebra and trigonometry, let me back off on that with trigonometry. Tangents, secants, things where you might divide by 0, those sometimes get a little bit iffy, okay? But for the most part, the functions you have dealt with are things that these limits just mean plug in the value. So for what we're doing here, if I say evaluate this limit, the first thing you try is always just plug in the value. So if I plugged in 1 squared minus 4 times 1 plus 7, I would end up getting, let's see, 8 minus 4, I would end up getting 4 as an answer. Boom, that's it, okay? If I came over here and it said, evaluate the limit as x goes to pi of cosine x, okay? I look and I see, and this is the important thing, am I dividing by 0? Am I taking a square root of a negative? Cosines don't do that. They're talking about x and y values that come out of angles on the unit circle. So try just plugging it in. You get -1. You're done, okay? So exponentials seem really intimidating, right? But exponentials are actually super nice. They're not doing any sort of division or square rooting of negative numbers. So you can generally just plug into those. So I'm going to do this limit as x goes to -2. And all I'm going to try doing is 2 times 3 times -2 minus -2 squared. That's going to be 2 times -6 minus 4. So 2 to the -10 power. If you'd like to write it as a fraction, that'll be 1 over 1,024. Okay. For various reasons, fractions are going to be better than decimals for a while here in calculus. Okay. So if you were writing a decimal, you know, it would be 0.0001, but we can be more exact than that for now. Okay. And then here's one with logarithms. Logarithms always seem super intimidating, but we try to just plug in. So we're taking the logarithm of 3 squared minus 8. Well, 3 squared is 9, and 9 minus 8 is 1. And the logarithm of 1, no matter what the base is, turns out to be 0. Boom, that's it. Okay. So insofar as evaluating limits with the basic limit laws, try plugging it in. If there's a division by 0, you have more work to do. If it's not division by 0, you just plug it in and see what you get, right? So here's where things start to get a little bit cumbersome. When you deal with a piecewise defined function, they will frequently have messy problems going on with them. So in this particular one, I hope that y'all spot that around x equals -1, there's going to be a difficulty, okay? And naturally, I'm going to ask you problems about the limit at x equals -1, because we're only really interested in the hard work, okay? So with this problem here, I'm going to have to give us this idea of what do I mean by limit as x goes to -1 plus. and limit as x goes to -1 minus. If the plus or the minus is after the number instead of before the number, it's regarding which side do we come in on, okay? So I'm going to jump over here and show you a different graph, and in retrospect, I just realized that I should have done this graph using the Desmos app. I did not think of it, okay. But seeing this graph here on the screen, it has things defined in a way that you're not used to doing. And that is that you can use these curly brackets and you can say, here's a condition on my x values. And then I put a colon and have my formula. And here's a different condition on my x values and a colon, and I give you this different formula. So those were the two formulas that I have taken off the screen there. And the thing that you need to spot that's going on is that to the left of -1, you are getting straight line. To the right, you're getting a parabola. Now, you can click on some of these points here and see what some of them are, but some of them will not allow you to label them. Okay, see the -1, 0 there. The reason it will not allow you to label it is that the function that we have here, we don't define the 2x plus 3 for x being equal to 1. Only x isn't. We don't define it for x being equal to -1, only for x being less than -1. Okay. So the thing that we're having happen on this function is that it is what's referred to as discontinuous. And to be super technical, the discontinuity is referred to as a jump discontinuity. So now, that should indicate to you that the plug it in method is a little bit suspicious there. So, however, there is a super nice principle that we have that you can do these limits in a nice way, and that is that if two functions are equal in some interval, then, and possibly not at the endpoint, then you can substitute that function in when you're taking the limit. So here on this one, when I'm taking this limit and x is going to -1 from the right, that means that I have x values that are greater than -1. So I'm allowed to take the limit as x goes to -1 from the right of the x squared plus x. And that is going to turn out to be equal to 0 because it's just +1 and then plus the -1. Okay. Then for the other one, we get the limit as x goes to -1 from the left. And that means that we have x's that are a little bit less than -1. And so we're allowed to use the formula 2x plus 3. So limit x goes to -1 from the left, 2x plus 3. Okay. And now I'm going to plug in the -1 and end up with just -2 plus 3 and get 1. Boom, that's your limit from the left. Now, you have to be cautious about something here. Every place that I'm doing these, I keep writing lim of something. Lim f of x, lim x squared plus x. I don't write just lim equals, because lim don't equal nothing. That, sorry, my rural upbringing came out there. So the lim is not equal to anything. The lim is a process that you're doing. So the limit of x squared plus x turned out to be 0. The limit of 2x plus 3 turned out to be 1. But you need to write that lim at every step until you get to filling in the answer. Okay. So last little bit there on this is evaluating f of -1. All that means is plug -1 in. I stopped to point this out because many times in algebra, people don't notice x equals -1 means use this formula. If x equals -1, you don't use this formula. You only use this formula if the x is equal to -1. So the f of -1 is going to turn out to be 0. We'd already done it before. When we talk about the idea of continuity, a function being continuous requires that the left-hand limit exists, the right-hand limit exists, and the function value is defined. And all three of those objects need to turn out to be the same thing. So here, we actually say that this limit, where it doesn't say left or right, it only says limit as x goes to -1, this limit does not exist. And that is because the limit as x goes to -1 from the right of f of x is not equal to the limit as x goes to -1 from the left of my f of x. Because those two things are not equal, we don't actually have a limit. We have left limits and right limits, but not a whole limit. So to have the whole limit, you have to have the agreement from the left and right. To get continuity, you also have to have the function value to exist and for all three to agree. So, all right. And I'm trying to peek over here real quick. Is there any other pieces that I needed to look at on that? I think that, I think that actually gets all of the pieces that we need for this. Cool beans. All right. So I will see you all in class on Wednesday, and ask any questions, and we'll get it figured out. All right. Oops. And then I should stop recording.